Okay, the first thing with the naming. Naming, we are going to look at the, you should know the concept of charges, okay? And you should know the symbols. And you should know the table, at least refer the D block elements, all the transition elements. And you should know that, they can exist in more than one type of positive charge, right? So for that, you're going to look at the table. I'm obviously not expecting that you memorize them, but in your handout, as you know, this is on the table, table 6.5, page 6. So, I mean, from time to time, I update the my handout. So, but anyways, this is the table 6.5. 6.5 table in the handout, okay? And this is on page 6. So anytime you're looking at the metals, right? Anytime you look at the metals, so for that, you're always going to check whether the metal belongs to the, whether it's a group 1A or it's group 2A, or it is group, the 3A like aluminum or the metalloids, all those the 3As and then the 4As, 5As, 6As, all those. All of them, the moment they are in the 3Ds, like the third, after the third, in the third period, after the third period, the fourth, 4S, the fourth period, you're going to check for, whichever ones. Now, let's look at these. Let's say, okay, the kind of questions that can be asked. I can say direct, simple one, like write the formula. So name is given to you, the name will be given, and you will be asked to write the formula. So simple questions can be name of the, like ionic compounds, like for example, iron, so hold on, it's not, let's just put it this way. So iron 3 chloride. So always remember that IDE is only when there are non-metals. Okay, so IDE is just for the non-metals. It is not, there's a difference between IDE and IT and 8. So IT and 8 are the, like the polyatomic ions. But this guy, just where you just have IDE, that means it is all non-metals will end in, non-metals end in IDE. IDE. Okay, so that means now this is chlorine. Chloride is coming from chlorine, and iron 3. So it's the simple part. What I meant here is that this represents the charges. So with that charge, what do we see? This is +3 charge. And you should know the symbol for iron, which is Fe. So now, that is one thing. So metal, the symbol for metal, the charges, if they are in the Roman numerals, so that is easy. You can just write the charges based on whatever Roman numerals you see. Chlorine, chloride, bromine, bromide, iodine, iodide, and then nitrogen, nitride, oxygen, oxide, and fluorine, what is the other one? Phosphorus, phosphide, and sulfur, sulfide. These are just a handful. So in this case, chlorine. Now, next thing you should know is the placement in what group. So this is in group 7A. So 7A, all the 7A elements have the charge of -1. Now, I'm asking you to use your notes, and I also ask you that on your periodic table right here in this periodic table, you should put the, the charges. So group 1A +1 charge, group 2A +2 charge, group 3A +3 charge, 4A +4 charge for the metals, right? 5A is -3 charge for the non-metals and +3 charge for the metals. Like bismuth would be +3, SB would be +3, AS would be +3, but nitrogen and phosphorus will have -3. Similarly, 6A is -2 charge. So for oxygen, sulfur, and selenium, -2 charge because they're non-metals. But tellurium and polonium +2 charge. And then fluorine, chlorine, bromine, iodine, group 7A, -1 charge. Okay, so here we have the group. So now just put here iron +3 and chlorine -1, crisscross. Now, on your exam, on your test, you have to show this because this is called working. You should have to show how did you get this answer. Okay, It's not a question of guessing. It's like showing how this is done. So FeCl3. This is the name. Okay. Now, question can be asked, what is the name of this? Another type of question can be asked. This thing can be given. So what is the name of this? Is it ferrous? Is it ferric? Is it something else? So the name of this would be, because it is in, so you're again going to refer to this table on 6.5. Remember, iron, you should know the placement. Where is iron? Iron is in the D block element. Okay, they can have more than plus type, more than +1 and +2, or +3 or +4, more than plus type charges. So in this case, when you check the metal in table, this table 6.5, you are going to get this as Fe. Oh, sorry. Okay. Fe, this is would be ferric, IC, ferric chloride. Okay. Now, ferric is a higher. Ic is for higher or larger number of plus charges with respect to iron. So higher plus state, you can say, or higher charges. Plus state means for you guys, let me just put this here, higher charges, higher number for plus charges, or larger number for plus charges. Okay, so plus charge. So it ends in ic. Okay, but if it was ferrous, then it would be FeCl2. So in that case, the name is ferrous. FeRrous. Ferrous chloride. CHLORIDE. And here, us terminology is for lower number of plus charges with respect to one specific element. Okay, so that's arsenic terminology, naming using the Roman numerals, right? Charges, all that. So just to summarize one more time, so we know that group number matches with the valence electrons and the charges. So group 1A plus 1 charge, 2A plus 2, 3A plus 3, 4A plus 4 for the metals. And this is where the yeah, so this is for the metals +3, and it can also be here. It can also have, because it's a 3 after in the third energy level, there is a D block. Remember, the 3D starts. So you will have to check the table for the elements. So here it can have more. From here it starts variable charges. So let's just put this here, variable charges, variable plus charge starts from here. Okay, and then you go down. Okay, 5A is -3 for the non-metals, such as non-metals here is the nitrogen and phosphorus. But for the metals, it is variable. Okay, metals, and then just continue to go down. Variable plus, so +3 charge. For the metals, it will be +3. Okay, then comes 6A is -2. -2 is for oxygen and sulfur. But for the metals, it will be +2. 7A, -1. That's for fluorine, chlorine, bromine, and iodine. And that ends here, actually. Let me just put this here. All these, so there is a set of variable charges that lie in this category. Okay, so that's the thing. And then, of course, the non-metals. So let's try the then, of course, the noble gases, the number 8A is 0. Okay, now, so based on this, so we know that if we are combining with non-metals, just the non-metals, the name is ending in IDE. But if you're looking at the polyatomic ions, and there are lesser number of oxygens, attached in a polyatomic ion, then in that case, the name is ending in ITE. But higher or larger number of oxygen, the ending is in ATE. Okay, so remember that. ATE is for like sulfate, like phosphate, like chlorate, nitrate, those names. So those will have higher number with respect to what element the oxygen is connected to. And then the lower number like sulfite, like phosphite, chlorite, so those things, okay? So now let's look at some of the other naming here. This was one type. This is, let's put this here, charges and symbol 1, 2, 3. Let's look at 3. Oh, sorry. Okay, number 3 is, third type is, naming is, let's say, let's look at a few of pop, a minute, lead, oxide. Okay, now in this case, they haven't mentioned whether it is +4 or +2, whatever. So if it's just this lead oxide just by itself, then we can write both, you know, or we can write one, depends. So depends on the multiple choice, what's available. So here we will see lead stands for Pb, and oxygen ide. Remember, it's just the oxygen by itself. So that's oxygen. Oxygen is in group 6A, and so the charge will be -2, okay? But lead, now from the table, because lead is coming in now you will have to refer to the periodic table as I'm going through this, because otherwise I'll have to move the screens back and forth, but refer to the periodic table as we speak. And so you can see here that what is the lead belongs to the period 4A, and it is in 1, 2, 3, 4, 5, 6, sixth period, and group 4A, and it belongs to that table. So it's in group 4A. So 4A, sixth row or period, let's put it PD. Okay, so it's belonging to, that means it's a D block, and so it can have you double check from the table. And I'm not expecting you to remember, so that's why I'm asking you to double check. But after some practice, you will remember that lead can exist in +4 and +2 state. Okay, so it can be +2, 4 and +2. Now we will have to write, since it's not mentioned whether it's lead +4 and +2, so we will have to look at both the options. So here PB, they changed the, okay, PB +2 and oxygen -2. Okay, so in that case, this number comes here and this one comes here. Now remember that we are looking at the simple whole number ratio, simple one. Okay, so we will have to simplify wherever we can. Simple whole number ratio. Okay, so in this case, we will have PB 2O2, but the simple whole number ratio is PB and O. Okay, so the name lead, so this reality is, this is lead 2 oxide. Okay, lead 2 oxide. And it will also have, the other name is plumbus, PLUMPOUS, plumbus. Okay, so did I mention this here? Oh, this was for the polyatomic ions. Yeah, variable charges here. The higher is us. The lower is us, and the higher is ik in this set. Higher and lower. So this is lower charge, and this is a higher charge, positive. Okay, now. Okay, so plumbus, us means lower charge. So that's a +2 charge. So lower charge, and that is lower implies +2 charge for lead. So if lead is in +2 state, then you would get that. Now, on the other hand, if lead is, if they say, okay, let's look at the choices, PB +4 and oxygen in that case -2. So again, show the crisscrossing. You have to show all the time. So this comes here, this one comes here, then this becomes PB 2O4. 4. And simple whole number ratio, 2 is to 4. The simple one is 1 is to 2. So the reality is this is PbO2. Okay, but it looks like PbO2, maybe Pb is in +2 state. That's just very misleading because it's coming from, actually, it's been simplified. So the real name is plumbic. Plumbic, Plumbic, plumbic oxide. Okay, this one is plumbous oxide, the lower one is plumbic oxide. Okay, and the other name is lead 4 oxide. Okay, so this type of naming can be like, I'm just covering it like the difficult ones I'm covering. Let's look at some. So any questions do you have right now? Any questions? Anyone? Just write it in the chat. All right. All right. Now let's look at the next one. With the, let's do a few practice ones. Like, let's say I give you some ions. Let's say calcium ion is given to you, right? And I say, write down the formula of calcium ion with nitrogen ion. Nitrogen is -3. This is given, okay? This will be given. So write down the formula. What is the formula? So what will you do? You are going to crisscross. This number comes here. This comes here. So this becomes Ca3N2. Okay? And because 3 and 2, 3 is to 2, cannot, because they're not even, right? Cannot be simplified. So we leave it as it is. Because 3 and 2 is like, cannot be, there's no common multiple or anything. So Ca3N2 is the formula. Okay, let's say if I give you, write the name of this compound, tin 2 sulfide. Oh, sorry, wait a minute. I give you this one, tin, I have to change now, tin, okay, SnCl4. SnCl4. So what is the name of this? Write the name. So, the worksheet that we gave you, it's, that practice, some of you did it very good, but this is the way you will do it. So what is the formula for, what is the name of this? Sn. Sn is tin. So you should know the Latin names, know the Latin name. That's where it gets tricky. Latin names. Okay, Latin names and symbols. And there are a handful of them, not many. Latin names and symbols. So I'll make a list of it right now here, just so you have it. So anyway, so tin is Sn, and then chlorine is Cl, chlorine. It's coming from, chlor. So leave it like that. Now you have tin. Just always check here the group number, and that group number relates to the charges. Okay, group number and charges match. Okay, so sorry, group, not 1A, but group number and the charges match. So chlorine is coming from 7A, so the charge is going to be -1. Okay, now tin, remember this is coming from top of tin. So that means for tin, it is going to be 4. Okay, +4 charge for tin. So now it becomes easy. So tin is +4 state and chlorine is -1 state. So the name of this one is tin 4 chloride. Remember, you will have to go back and forth with chemistry. When the memorization, you remember, but it's not possible to memorize things, especially, in a short time frame. So, or maybe it takes longer for some people. It's fine. All this is fine. So just make sure that you're always checking the table. Where is tin placed? Now, tin is a like what is it called? A post-transition element, and it will have a D, right? So it will have a variable oxidation state. In other words, variable plus charges. So you will always have to check in the table so you can see which one plus or what is the, whether it's +4 or +2, because remember there's cancellation also happens, which I'll show you in a minute. Okay, so anyway, so this is tin 4 chloride. The other name is, it is larger, right? Stannic chloride. Okay, stannic chloride. So this is the way, you will get it. Let me see if I can open up the handout for you. Just give me 1 minute. Okay. 1 second. Let me just pause the recording. Okay. So the middle ones in the periodic table will always have +2 charge, and they can have more. Okay. Middle one is the D block. Yes. Yes, Jessica. The middle ones, the transition elements are the D blocks. Okay. These also have the D orbitals, the green ones. You see, these are the post-transition elements. So these post-transition elements can also have variable plus charges. So like gallium, aluminum, gallium, indium, thallium will have +3 because they're in group 3A. Plus, you have to check if there is more. Like tin, like group 4A, carbon, silicon, germanium, tin, lead. So they will have +4 charges, and they can have +2 charge and +4 charge. Bismuth, group 5A will have +3, and it can have more, which is +5, and so forth. Okay, these guys you have to check if they don't have, now the minimum would be +2, all of them, and they can have more. These guys are different. Group 1A, only +1 charge. Group 2A, only +2 charge. Okay, so anyways, now which table I'm referring to again and again, as I said, this was the table you will go to. This is the table. Okay, so check here when any metal is given to you. If it's not group 1A, group 2A, then check here. And you will see which elements we're talking about. And they have given you the Roman numerals, but check this. Please note, always, please note, lower charge state ending in us and higher in ic. Okay. Now, some of them could sound weird also, like manganese. So manganesus and manganesic. It kind of sounds, name is not very, nice, doesn't sound nice. So we just, use the Roman numerals in that case. So anyways, so that's one thing. Next is, let's look at the scenarios where you have some other types of name. Let me give you another one is bismuth phosphide. Bismuth phosphide. And so here, let's do bismuth 5 phosphide. So write the formula for this one. Bismuth 5 phosphide. So bismuth 5, what does that mean? That means it's bismuth with +5 state. Now phosphide, IDE, that means it's just phosphorus. Okay, it's just phosphorus, and it's phosphorus here, and ID is just like, it's just a non-metal. Group 5A, phosphorus is in group 5A, charge is -3. So here you have phosphorus -3. And then you write the formula, crisscross, this comes here, and this one goes here. Okay, and so the name is Bi3P5. Okay, this also means that for every like for that, we need 3 in order to form the bond. This is something that I missed in the class, that in order to form the ionic bond between these, so 3 bismuths are needed and 5 phosphorus are needed. So this means 3 atoms of bismuth and 5 atoms of phosphorus will only make the ionic bond. Okay, will only make ionic bond only when this combination is there. If it's less or more, it won't work. Okay, so that's what this is. Then let's look at now with the polyatomic ions. Let's look at that. Now for the polyatomic ions, where is the polyatomic ions are, that's the only thing. So you will have the table. See, ideally you have to memorize the polyatomic ions. Okay. So like chlorate, phosphate, iodate. Oh dear, why is it not loading? Okay. That's the only thing, again and again. Okay. Now you have to memorize the polyatomic ions, but for now you can just refer to these. The good part with polyatomic ions is their name doesn't change. It stays the same. So you just have to worry about the names of the metals. Okay, so now here is the list of polyatomic ions. Okay, now so carbon based, chlorine based, sulfur based, phosphorus based, polyatomic ion, nitrogen based, and hydrogen based. So you see that we talked about eight and eight, the difference between eight and eight for the based with respect to nitrogen. Lower number of oxygens, eight. Higher number of oxygens, eight, with respect to nitrogen. So NO3 is nitrate and NO2 is nitrite with a -1 charge, both of them. However, in this case, if you look at sulfur, SO4 is sulfate. SO4 is sulfate. And, oh, where is it? Okay, SO4 is sulfate and SO3 is sulfite. So don't go by this fact that 3 is always going to be 8. No, it's with respect to which element oxygen is bonded to. So sulfate is SO4 -2 charge, and sulfite is -2 charge, but with 3 oxygen. Same story. Look at the phosphate. Phosphate, because remember we talked about yesterday that sulfur and phosphorus have a capacity to make more bonds with oxygen. So sulfur can make 2, 4, and 6 bonds, right? And phosphorus can make 3 bonds and 5 bonds. So based on that capacity, they can have 4 oxygens. So phosphorus can also bond with 4 oxygens, -3 charge in this case. Sulfate is -2, but phosphorus is with oxygen is -3 charge, and the name is 8, phosphate. But phosphite is less oxygens, but the charge is the same, -3 charge. Okay, so this is something that comes with time and practice and memorization. But for now, at least double check, refer to these tables when you're doing the problems. Okay, so with practice, you'll get it. Takes time a little bit. Okay, but anyway, so let's look at now the chlorate. Similarly, chlorate is ClO3. Now this is the difference. Chlorate is ClO3 -1, but remember but ClO4 got discovered much later. So now we cannot, ideally ClO4 should be chlorate, but then once ClO4 was discovered much later and ClO3 was already in practice, so we decided to stick to this name for chlorate, ClO3 -1, and we decided to name ClO4 as perchlorate. So per is higher than chlorate. Similarly, ideally ClO should be chlorite, but then ClO2 was discovered earlier and ClO- was discovered much later. So then we said, okay, we can't change the names that once they're already given and name is set. So what do we do then? We said, okay, later modification, chlorite became hypochlorite. So less than chlorite. Less than chlorite is hypochlorite. So less than 2 is 1. So that's why hypo. So that chlorate thing with chlorine is a different naming set. Okay, so that's the thing. And same is the case as we talked about hydrogen, hydroxide. Hydro is written first, like naming, but the formula is OH. Again, this is an old name. So it got its name, it's stuck with this. And like I said, HCO3, when hydrogen comes in front of carbonate, the old name is bicarbonate, which you see in like, soda bicarbonate, which we see in the commercials or whatever molecules, I mean, the compounds that are sold as chemicals. But hydrogen carbonate is like a little bit more appropriate. Hydrogen comes first and carbonate later. Similarly, hydrogen phosphate. Okay, so these things. Now we have this sets again, other types are like perbromate, bromate, bromide, hyperbromide, same as the chloride and iodide. So all this story with the halogens, remember, chlorine, bromine, iodine can make 2, 4, and 6, 1, 3, 5, and 7 bonds. So that is how they end up attaching to more than one type of oxygens, number of oxygens. 1 oxygen, 2 oxygen, 3 oxygen, 4 oxygen, and their names, all of them are the same, per and hypo, and then the other aid and ide. Next is the nitrate, nitrite, and cyanide, and thiocyanate. Now, thio is attached with, now cyanide is CN, and unfortunately thiocyanate does not have oxygen. Eight blends with oxygen. There's no oxygen here in SCN, but the name is like that. So just take the names as you see them here and go by the flow of naming. So let's name some of them. So let's say you have calcium nitrate. Calcium nitrate. Now, in this case, nitrate is nitrate. So just write down formula: nitrate, NO3 minus 1. So at least this much you can do. You can refer to the table. Ideally, you should memorize, right? This has to be memorized. But for now, just refer to that table. And calcium is Ca. So symbol is Ca. Group 2A. So the charge is +2. Okay, +2 here and +2 here and a -1 there. So now, anytime more than one charge, when the charge that is crossed over charge is more than one, what happens then? Then we place the polyatomic ion in the parentheses or brackets. So recognize that this is a polyatomic ion. And we are bringing in more than one type of charge, more than one charge, that is +2 charge, plus like 2 is more than 1. So 2 is more than 1. 2 is more than 1. Therefore, we place nitrate in bracket and put 2 outside. So we place it like, placement is like that. So rest is easy. Ca brackets NO3 2. Okay, not -2, regular 2. So this means that one atom of calcium will bind with 2 polyatomic ion, 2 nitrate ions. Okay, so if you look at, there's some let's look at Lewis structure. So here is calcium. Let's put it here. Sorry. So Lewis structures a little bit. This was in the book also. I forgot to mention this in the class. So here calcium 1. So these are the 2 + 2 charges, means there are 2 valence electrons. Okay, so these are the 2 valence electrons. 2A have 2 valence electrons. So this is the Lewis structure for calcium. Okay, so this means now it is going to bound. So one goes to this nitrate NO3. -1 means like -1 charge, and NO3 -1 charge. So this and this will bond. Like, so this connection will be made like this. Okay, so this is how you have 2 nitrates connected to 1 calcium. Okay, similarly, if you have, like, say, aluminum, let's say aluminum +3, or let's say aluminum oxide, okay? So aluminum oxide, aluminum group 3A, okay, +3 charge, oxygen 6A -2 charge. So here is aluminum Al, and here is oxygen -2 +3. So this means now when you do the crisscrossing, this becomes aluminum Al2O3. Okay, so this means aluminum with the +3 charge, 3A will have 3 valence electrons, 6A will have 2 valence electrons. So here are, how do I show this? 1. So this means 2 aluminums and 3 oxygens. This means that 2 atoms of, and you're going to study this more, then it's actually moles, but for now 2 atoms of aluminum will bind to 3 atoms of oxygens to make a stable molecule. Okay, so in this case, how does it show? Aluminum, 2 aluminums like this, and 3 oxygens. So 1, 2, 3, 1, 2, 3. So here is 1 oxygen. This is another oxygen, and this is another oxygen. Oxygens have 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Oxygen needs 2 more, right? And aluminum is better giving away those 2 electrons. So oxygen gives these 3 electrons. So oxygen, aluminum gives 2 to this oxygen, and then it gives 1 here, and this guy gives 1, and then this one gives like that. So when that happens, aluminum will acquire, aluminum gives -3 electrons, right? All the 3 electrons, each aluminum is giving 3 electrons, and aluminum acquires a +3 charge. Each oxygen, although 1, 2, 3, 4, 5, 6 oxygens are, 6 electrons are being given, but each oxygen can only take 2 electrons. So that's how this acquires a -2 charge, 1 oxygen. But to make a stable thing, because then 1 leftover electron, where is that going to go? That is why we need 3 oxygens to balance all the electrons, giving and taking of the electrons. Okay, so you will study this more, like where they do the balancing of the electrons, in other higher chapters, but higher courses actually. But let's look at, so this one was 8. Let's just do 2 more polyatomic ions. So this was 7, and then we will move to the next part. This was 8, right? 9. So I'm using the Roman numerals here. Okay, now let's do with, let's say, ammonium, phosphate. Okay, so phosphate is phosphate and ammonium is ammonium. No big deal. So write down ammonium NH4 the way it is with +1 charge. Phosphate, write down the way it is, PO4, -3 charge, and crisscross. This number comes here and this number comes here. We do not write for 1. Okay, so don't write 1. Don't leave it blank. But for 3, we will write. So now we are moving 3 down to ammonium. Ammonium also is a polyatomic ion. So this guy will now go in brackets. And phosphate is 1, but ammonium. So this means that 3 ammoniums are needed to balance out with 1 phosphate. So you can see it. Phosphate is PO4 -3 charge. So this 1 charge, another charge, another charge. And then comes ammonium, NH4 +1. This is another NH4 +1, and then comes another NH4 +1. Okay, so this and this will connect. This and this minus, this is a minus charge. This is electron, this is minus charge. This will connect. This and this will connect. And then this and this will connect. Right? So you see that these minus charges get neutralized this way, plus charge. So these are all minus. This means -1. This is -1 electron minus. So these are the 3 electrons. So we write like that. So this is how they balance out. This is +1, +1, +1. Okay. All right. And then now to the other one, sulfate with aluminum sulfate, ALUMINUM, and sulfate, SULFATE. So aluminum is just aluminum, right? Symbol is Al. Group 3A +3 charge, right? 3 valence electrons. Sulfate, SO4 -2. That is what it is. So this is +3, and crisscross, this number comes here, and this number goes here. And what do you get here? Al2, because it's aluminum by itself. It's not a polyatomic ion. So we just put Al2. And then this is the polyatomic ion, SO4 and 3. Okay. Now, because aluminum is in group 3A, so double check. It's not like, it does not have any variable charges. If you look at the check, always check that table for variable charges. So which table is that? This is table 6.5. Okay. Table 6.5 for variable charges. So just to double check. Otherwise, with practice, you would know aluminum is in group 3A, it's on the top, and so forth. Okay.
Professor, I put
so that's the deal with the naming and writing the formulas and why certain things happen. So we did quite a bit here. If you guys have any questions on this, do you guys have any questions? Yeah, I see some people here. So so Vanessa is asking I felt okay, but now I'm a little confused because aren't we supposed to separate the valence electrons when writing the Lewis structure? So these are, which one? I believe you're talking about these ones. Are you talking about these? Vanessa? Hello, Vanessa? Yes. So these are the Lewis structures, and these are aren't these the valence electrons? Aluminum has 3 valence electrons. This aluminum has 3 valence electrons. This oxygen has 3 valence electrons. These are 3 valence electrons. These are 3 valence electrons. So what is mixing here? Maybe we can separate them evenly. They are separated. So what do you mean? Like writing them, like in what way separate them evenly? They are separated. I'm not understanding. You mean like write like this? Oh, you mean like write like this? AL like that? This is how you mean? Yeah, you can do that way also. Doesn't matter. You can do, even in any case, it is just going to be 3 electrons. Okay? It will be 3 electrons, but you can place them. Then in that case, you will have to place oxygen. You can't place oxygen here on the top, right? It has to be somewhere close by. So I just, for the space, so you can put oxygen here, 1, 2, 3, 4, 5, 6, and you can show like this. You can also show like this. You put here, and then you will have to show this one going like this. Okay, you got it? But the other one is still like, that's what I was saying, that this guy is left. So that is why you need another aluminum and you need that other oxygens to balance. Okay, yeah, all right. All right, you can, so this is also okay. All right, next is, now we are going to look at the Lewis structures. So second part is Lewis structure. So we covered, these were all ionic compounds. This was ionic compounds, and there's something else, the naming. Yeah. So other type of naming is for the non-metals naming, the non-metals. So that is kind of easy. Non-metals will be so there are diatomic molecules. Diatomic means the ones that have the same atoms. So same atoms will have the name is just the name of the element. Like for example, H2, okay, hydrogen, O2, oxygen, N2, nitrogen, F2, fluorine, Cl2, chlorine, Br2, bromine, and I2, iodine. Okay, so these are just a handful of nonmetals, and that's just the diatomics. So this is their name is, matches with the name of the element in the periodic table. So that's one thing. Next thing is other types. You are going to use the di, tri, and tetra terminology. So once again, if you see here, this is the, where did it go? Okay. Once again, you will see here, I have placed this just in case you forget, but this is where they are placed. So you can see, okay, right here, all the diatomic molecules and all the, the prefixes, the mono, di, tri, tetra, penta, all that is also here, just in case you forget. So we have them here. Okay. Next is, you see, let's say, for example, let's say P2O5. So this would mean diphosphorus. There are two phosphorus. So it's very important to recognize the symbols. Diphosphorus, pentaoxide. Okay, pentaoxide. So that's the name. Okay, but some of the other names you should just know. CH4 stands for methane. So this is something you just have to memorize. Okay, common names, right? Methane. Then NH3, just memorize this. This means ammonia. Ammonia. At least these common names you should know. Okay. Um, Otherwise, it is like mononitrogen trihydride. Like, if you have, like, for example, another one is, let's do carbon I4. So this means carbon is just, so we don't write mono carbon, we leave it carbon, but there are 4 iodines, so tetra iodide. Okay, iodide. Okay, right. Now, next comes the third one, is the Lewis structures now. So my recommendation is the nomenclature worksheet that I have given you. If you keep practicing that one, like, and sort of memorize the periodic, the polyatomic ions and the symbols of the elements, and just know, where, which element is kept in the periodic table, so that you can kind of remember their charges, or, put the right charges, crisscross, and then you'll be done. Okay. So now we are going to look at the Lewis structures. And in this case, the Lewis structures is with where the non-metals are attached. So remember that the first one was the ionic bonds, when the metals and the non-metals are connecting right here. So we talked about here the ionic compounds. Ionic compounds. So how are the ionic bonds formed, or ionic compounds formed? By the transfer of electrons. Transfer of electrons, and that is between the metals and the non-metals, and the metals and the polyatomic ions. So those things, so that you have seen. Now these guys are formed by the sharing. So this is the covalent compounds, covalent and then by sharing of electrons. So no transfer, no charges. In this case, sharing will not bring no charges. Okay, but we do consider the valence electrons. Okay, so valence electrons come from the group numbers. Okay, group numbers. So once again, very simple. Group 1A, group 1A, 1 valence electron. 2A, 2 valence electrons. 3A, 3 valence electrons. 4A, 4 valence electrons. See, charges are different. 5A, 5 valence electrons, and not 3 valence electrons. No, 5. That we were talked about the charges. Charges will be -3 or +3. 6A, 6 valence electrons. 7A, 7 valence electrons. And 8A is 8 valence electrons. Okay, so that thing. And look at the bonding. So this will make 1 bond, and 2 will make 2 bonds, 3 makes 3 bonds, 4 makes 4 bonds, 5 makes 5 bonds, 6 makes 6 bonds. Sorry, wait a minute. 6, sorry. I also went by the wrong flow. 3 bonds, 2 bonds, 1 bond, and 0 bond. But that is when they are bonded to less electronegative atoms. Remember that. Nitrogen actually can make 3 bonds, and nitrogen can also make 4 bonds. 4 bonds, like in ammonium, it's making 4 bonds. Okay. Then nitrogen and phosphorus. Phosphorus can make 3 bonds when it's bonded to less electronegative atom, but it can make 5 bonds also when it's bonded with oxygen. Okay. Sulfur will make 2 bonds, but sulfur can make 4 bonds and 6 bonds. Sulfur, then comes fluorine, chlorine, fluorine, chlorine, bromine, and iodine. These guys will make 1 bond. Okay, these are the bonds we are discussing here, bonds. Okay, but chlorine, bromine, and iodine can also make 3, 5, and 7 bonds. And then comes xenon. Xenon will make 0 bonds, but xenon can also make 2, 4, and 6 bonds. So in what conditions they are making these excess bonds? 5 bonds, 4 bonds, 6 here, and then this one 3, 5, 7, and then 2, 4, 6, when they are bonded with oxygen. Okay, when they're bonded with oxygen, only then they can make, like, or a higher electronegativity, or wherever there is a more electronegative atom, then in that case they expand their bonding. Okay, so now let's look at the bonding of H2S versus SO2 and SO3 minus 2. Okay, I'm going to do these right first. Let's do this. H2S, first of all, H2S. Now, H2S, remember, you're going to follow the steps, always follow all the steps that are listed in the handout. Okay, listed in handout. What are the steps that are listed in the handout for making the Lewis structure? You're never going to go wrong. So, excuse me. So now here you will see in this modules, here, handout, and so this part that we talked about, covalent bonds, making different types of, bonding capabilities of the nonmetals. And then you look at the steps in drawing the Lewis structure. Okay, this one. And then if you look at it, I've written, remember, the same thing that we captured just now, that chlorine can make 1 bond, but chlorine can make 3, 5, and 7 bonds. I have also put here, just in case, So refer to all this information that is given to you. But this is your steps, okay? So let's look at these 3 situations. And here we have the first one, H2S. Always, so one question is going to be, find the total valence electrons, always total valence electrons. So hydrogen is hydrogen. There are 2 hydrogens, there's 1 sulfur. So one question will be like that. So hydrogen has 1 valence electron and sulfur is bringing 6 valence electrons. Okay, so 2 electrons coming from hydrogen and 6 coming from sulfur. So we have 8 electrons here. Okay, now in this case, what do we see? We see that 8. So we are going to, so that's 8 electrons we have to keep. So this is one part. Second part is which one is going to be in the center. This is the most important part. Never. So if you can even remember this, I see students putting hydrogen in the middle. No, never. I'm putting this in red. Never place hydrogen in the center. Okay, always. So central atom is determined by the bonding capabilities. So bonding is depending upon how much, bond capabilities. So the capability of sulfur is obviously more. So hydrogen can only make 1 bond. So why will it be in the center? Center will be more bonding, right? Sulfur can make 2 bonds, will make 2 bonds here because hydrogen is less electronegative than sulfur. So therefore, sulfur will only make 2 bonds. Sulfur can make 4 and 6 bonds, but it's just, it is connected to less electronegative atoms, only 2. So place sulfur in the middle. That's the third step. And that's the beginning of your working. Place hydrogen here. Next hydrogen here. Okay, connect them with a single bond. Connect them with a single bond. 1, 2, 3, 4. Okay, now, so count the bonds that the electrons that got used in making the single bond. So we had 8 electrons total, and out of those total, 4 electrons got used in making single bonds. So now what is left? In this case, you are left with 4 more electrons. Now, just because, so I just want to clarify this, just because your handout stays, I don't know if I have mentioned this here. Let's see, let's double check. Handout states that, the steps state that each single bond uses 2 electrons, okay? Count the total number of electrons used in making the single bond, and then subtract these from the total number of valence electrons, which is 1 in this case. So remaining electrons, place the remaining electrons on the outer atoms except hydrogen. Okay, very important. Place the remaining electrons on the outer atoms, but not for hydrogen. Okay, we place them in pairs of 3, like 2 dots, 2 dots, 2 dots, like that on the outer atom, so as to fill the octet. Okay, so that's the important part, and that's what I've seen. Any remaining electrons, and students start putting them on hydrogen. Do not do that. You don't need it. You're done. Hydrogen wants to look like helium, and hydrogen is looking like helium. This hydrogen has its 1 electron, but it's sharing one of the electrons from sulfur, so it has 2 electrons, and it's satisfied. That's happy. Hydrogen is making 1 bond, happy. So this is the reason why. So that's practice, don't it? So now the remaining electrons go on the central atom. So not on the hydrogen. So like that. Place them always in pair. So these are the lone pairs. Now, here, place them like this. Lone pairs always stay on the top and the bonded atoms are pushed down. Remember, it's the VSEPR theory. Valence shell, electron, pair, repulsion. So repulsion, these bonded atoms are not liked by the non-bonded atoms. Non-bonded. So these lone pair mean 2 electron are shown like this. These are the 2 electrons, and these are also called a non-bonded. Non-bonded. They are not bonded. So they push the bonded. So these are bonded. These guys are bonded, and that one is also bonded. So bonded atoms or bonded electrons are like pushed away. So bonded electrons or bonded atoms, they are pushed away by the lone pair. So that's why lone pair will stay on the top. There is a repulsion between the bonded and the non-bonded. That's why. Okay. Now, anyway, so that's the right structure. Now let's look at the shape, and now let's look at the polarity, both of them, shape and polarity. So very easy now. Number 1 is the shape. So for the shape, you're going to look at the type. Very easy. What is easy? Now, S sulfur is A because it's a central atom, and hydrogens, there are 2 hydrogens and they are equal to X. So we look at the AX. So it's the AXE type of terminology. So X is there are 2 hydrogens. So, and then there is lone pairs. There are 2 lone pair, LP, lone pair. Okay. So this becomes AX2E2. AX2E2. Okay. AX2E2 means that A is for sulfur, X2 is the 2 hydrogens, E2 is the 2 lone pairs. That's how. Now you look at the table for that. So for that, you're going to consider the table, and you just look at the molecular geometry. For your course, it's molecular, but if there's somewhere in the question the electron geometry is given, so you look at the question and go from there. So molecular geometry simply means shape. Okay, it's the overall shape. So here, what are we doing? We are looking at this table, the big table that says shapes, and all you do is now look at the right here, AX2E2, this one, AX2E2, okay? And AX2E2 is, don't worry about these 3 tables, this is not for you. Tetrahedral and bent. Tetrahedral is the electron group geometry. Molecular geometry means shape, and that is bent, okay? So that implies to bent. So this would be a bent molecule. This is in this case, it is bent. So this is in this case, it's implying bent. Okay. So that's the shape. You're done very fast. Now comes the polarity. Now very easy this also. Remember, I told you, now there are two types of polarity. One of them is the bond polarity. Bond polarity is the individual bonds, okay? Individual bonds. And then there is a net polarity. Net polarity is the molecular polarity. Net polarity is the sum total of all the bond polarities. Sum total of bond, individual bonds, sum total of bonds, bonds polarities, and here, what do we see? Sum total of bond polarity, and in this case, this means the molecular polarity, the molarity of the molecule, molecular polarity. Okay, so you have to look at both. Now, easy thing in this case, because in this case, if whenever there are lone pairs on the central atom, lone pair on the central atom, molecule is always going to be polar. Lone pair on central atom, the molecule is always going to be polar, always. So this is a polar molecule, okay? Besides that, if you look at sulfur 2, and you have this hydrogen, and you have this hydrogen, if you look at the individual bonds also, look at the individual bonds, okay. So for that, you're going to look at the electronegativity values. So look here, electronegativity values are here, okay? The hydrogen has 2.1 electronegativity and sulfur has 2.5. So 2.1 and 2.5, difference is minus. So the minus is 0.4. 2.5 minus 2.1 is 0.4, and it's falling right where it's a polar bond. Okay, polar covalent. It's like the start of that. That means the charges are unequally placed. So this is going to be in a, like there's going to be slight negative and a slight positive charge. Okay, so here you have, in this case, this is sulfur 2.5, hydrogen 2.1. So this is 0.4. So this is a polar covalent bond, polar bond. Covalent means, sharing. So this is a polar bond. And so with that said, we will have delta negative, delta positive on this hydrogen, delta positive here, delta negative here. Okay, so this means that the electrons are pulled towards sulfur. The electrons are pulled towards sulfur. And we also have lone pairs. Lone pair are these electrons. So that makes it very, very polar. Okay, so that's one piece. Now we are going to look at the next one, which is sulfur dioxide. Now let's look at the next example with sulfur dioxide. Sulfur dioxide. So sulfur, group 6 has 6 valence electrons. There are 2 oxygens. Each is bringing 6 valence electrons. And you add these. So 6 plus 12 is 18. So total valence electrons are 18. Okay, total valence electrons are 18. Now, we are going to place sulfur in the middle because sulfur can make 2, 4, and 6 bonds, and oxygen can only make 1 bond. So these, because of the bonding capability of sulfur, and sulfur is connected to oxygen, so it is going to make more than one type of bond. So it can make 4 bonds, it can make 6 bonds. So let's see, because it has that capacity. So we'll place sulfur in the middle. Oh, sorry. Let's put it like this. Okay, sulfur goes in the middle, and here comes oxygen 1 and other oxygen. Okay, connect them with a single bond, this single bond, and 1, 2, 3, 4. 4 electrons got used up. So 18 minus 4, and we are left with 14 electrons. Now, the rule says from that table, once again, let me just show you that table is, so you don't forget. That's why, although it's, where is, okay, one more time. So I'm not going to show this again for the next example, but you should always refer to these steps. You're never going to go wrong. Always refer to these steps, okay? And in your handout, they are on page 10, but these are the steps in drawing the Lewis structures for 3 or more atoms. So if you just follow these steps, when you're practicing the Lewis structure worksheet or your homework problems, then, that'll be good practice. Anyways, so these remaining 14 electrons, because it's oxygen, so we are going to place outside. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Okay. Remaining, we place first only in pairs, only in 3 pairs. You place them, 3 pairs on each outer atom, not more than that. Okay. Only on outer atom, 3 pairs. And then any leftover, these are the ones that were left over. Left over go on the central atom. Okay. Now, here, what do you see? In this case, you have sulfur. Now, you're going to always check. That's why I'm saying you're never going to go wrong if you check. You're going to check for, first is the need to make the bonds. That always takes a priority. Need for bonding. Okay. So oxygen wants to make 2 bonds and it's not making 2 bonds. So oxygen is very unhappy here. Okay. Oxygen is very unhappy. And sulfur can make 2, 4, and 6 bonds. So sulfur is happy. Sulfur is very versatile. Sulfur is happy. It's making 2 bonds, right? But let's look at the next piece. You should also check the octet. But we know that these guys, remember this list I made here for you, these guys, in this case, are defying the octet. They are, when they are bonding with oxygen, they defy octet. So they won't follow the octet rule. All right, now we have, in this case, the octet. Sulfur can defy the octet, but oxygen, look at oxygen. Oxygen is making oxygen has 1, 2, 3, 4, 5, 6, 7, 8 bonds. Oxygen is satisfied. 1, 2, 3, 4, 5, 6, 7, 8 bonds. So oxygen is satisfied in both the cases. So oxygen is getting 8 electrons. So oxygen is happy from that perspective, although it's aspiring to have 8 electrons, 2 bonds also, if it can get. Sulfur can defy the octet. At this point, sulfur has 1, 2, 3, 4, 5, 6 electrons only. So sulfur is making 2 bonds, but its octet is not met. Okay, so octet is not met. So it's not met. So it's not making that. So from that perspective, it's unhappy. Okay, so we have to do some rearrangement. It's very important. So this is only working shown. This is not the full complete structure. This is only, a step in showing the working. Okay, so this is incomplete structure. So that is why we will have to do these steps. So what are we going to do next is the rearrangement. And in the rearrangement, what are we doing? We are now looking at sulfur is here, oxygen here, oxygen here. This oxygen has 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5, 6. Somebody has to give the electrons so that, so here we see this oxygen gives 2 electrons. And then when that happens, this oxygen can also give 2 electrons. And when that happens, these are actually coordinate covalent bonds. Covalent bond. Coordinate covalent bond forms when 2 electrons are donated, are given by 1 atom. So oxygen is giving those 2 electrons. So now we have sulfur, and now we have this oxygen, oxygen, and double bond. Now it has this double bond, but only 2 here, 2 pairs here. Now it's made this double bond right here. And this guy stays on the top. That doesn't change. That one is there. Okay. And I made it like this bent because remember the lone pairs don't like the bonded atoms. So the lone pairs will be on the top. Now what do you see here? In this case, oxygen has 1, 2, 3, 4, 5, 6, 7, 8. 8 electrons, and oxygen is making 2 bonds. So very happy state for oxygen. Okay, this oxygen also has 1, 2, 3, 4, 5, 6, 7, 8 electrons, and it's making 2 bonds. So this oxygen is also very happy. Okay, and besides that, the sulfur 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Sulfur is making 4 bonds, and when sulfur is making 4 bonds, it defies the octet. It defies octet. Okay, it doesn't follow the octet rule. In this case, it cannot. And that's okay. I mean, sulfur has a capability to do that because sulfur has d orbitals. Okay, d orbitals means that internal jumping that gives that expanded capabilities. More room it has got to accommodate the 2 electrons given by oxygen. So that's the thing that now this is a perfect structure. And if you look at it, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. All the 18 electrons have been accounted for. Okay, so that's how you will draw this structure. Now shape and polarity. So there is a lone pair on the central atom. Lone pair on the central atom. So this becomes polar. This is a polar. Overall molecule is polar molecule. All right. And then you shape. Now in the shape, remember, it's sulfur and oxygen and then the lone pairs. So there is 1 lone pair on sulfur. There are 2 oxygens, right? 2 oxygens, and there's 1 sulfur, of course, the central atom. So this is AX2E1. So if you look at that shape, AX2E1, look at the table. For the shapes AX2E1, what is that? AX2E1. Okay, AX2E1. You know, some of you have not seen this type of, terminology and all that. If you're able to figure out on your own, it's fine, whatever method you learn. But this is one method of identifying the shape. Fastest, quickest way of doing it, AX2E1. You come here and then you see this. This is electron group geometry is trigonal planar, but the molecular geometry is bent. So here, bent molecule shape. But electron, remember, as I explained, the electron group geometry. Electron group geometry is like internal when you go inside the molecule, but molecular geometry is outside, external. So from outside, external. So from outside, it looks bent, but internally, it's different. Internally, it is, what did we look at? It was trigonal planar. Is that? It was trigonal, AX2E1, trigonal planar. Okay, so let's see what trigonal planar looks like. Okay, here is the trigonal planar. So sulfur here, oxygen here, and these are the lone pair planar. So it's like a plane, like a triangle, like a pizza shape of pizza. Okay, there's How do you do this? Okay, so this. Okay, so this is like a pizza. So, so trigonal, planar. Like a pizza, slice of pizza slice. Flat. Okay. So that's what we did. Shapes, polarity, structures. And now the last one is sulfur trioxide. Sulfur trioxide. Okay, actually, instead of sulfur trioxide, let's do this one. Actually, I have made the sulfur ones in a video also. Let's do phosphite, PO3 minus 3. Okay, it's really better. Okay, because it's a sulfur, it's the same story. Okay, so we did 1, 2, and 3. Let's do for phosphite. PO3 minus 3. Okay, so here, phosphorus. So phosphorus is group 5A. Okay, 5A means 5 valence electrons. Oxygen is group 6A. Oxygen is group 6A. So it has 6 valence electrons. So there are 1 phosphorus and there are 3 oxygens. 1 phosphorus, 3 oxygens. So we have 5 phosphorus here. So it's got 5 electrons from the first one and 18 electrons here. And then we have plus 3 charges. Okay, so there are 3 charges. And these charges are negative charges. So that means you will have to add 3 electrons also. So now you add. So 14, right? 6 3s are 18. And phosphorus is 5. 7, 8, 14. Oh, no, sorry. 14 here, 24. 24 electrons. Okay. So these are the total valence electrons. So there is going to be a question like find the total valence electrons in phosphate, sulfate, and so forth. Okay. Now we have to identify the central atom. So obviously oxygen, in this case will not be because phosphorus can make 3 bonds, but phosphorus is bonded to oxygen when bonded to oxygen. Okay, then phosphorus can make 5 bonds. It will expand its capability. So oxygen can only do 3 bonds. Oxygen can only do 2 bonds. Sorry, 2 bonds. My mistake here. Sorry, 2 bonds. Okay, now, so we will put phosphorus in the middle and we are going to place oxygens on the side. Now there are 3 oxygens. So just make sure that you place them like in some kind of a symmetrical order. Okay, so this is symmetrical. This is symmetrical. Okay, next is connect them with a single bond. And here you have 1, 2, 3, 4, 5, 6. 6 electrons have been used. So minus 6. So you have 18 electrons left. So the remaining 18 electrons go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, and 18. 18 electrons have been used up. Okay. So once you do that, you're going to again check. So obviously, it's obvious now by this time that oxygen has the octet is met, but it's not making 2 bonds. Okay, so its octet is met, but it's not making 2 bonds. Phosphorus, on the other hand, 1, 2, 3, 4, 5, 6, octet is not met, and it's making 3 bonds, which is fine. For oxygen, it's fine. It can make 3 bonds, so which is okay, but its octet is not met. So in other words, they are not satisfied. So what are we going to do now? The thing is, PO3, did I get this right? Yeah, so in this case, there are three so somebody will have to carry those negative charges. Okay, so we have these 3 negative charges, PO3 minus 3, and phosphorus. Once again. All right, I made a mistake in counting. I'm sorry. Okay, so 5 here and 5, so 5 from the phosphorus, 18, 19, 20, 21, 22, 23, 24, 25, 26. It's not 24 electrons. I'm so sorry. It's 26 electrons. Okay, that's why I thought, okay. Yeah, 24. No, it's not 24. It's 26. So 26 minus 6. So now 8. Now we need to place. So this is changes. Oh, I think I need a little break here now. Okay, 26, 20 electrons. Okay, so we placed 18 on the oxygen and the remaining 2 go on phosphorus, like that. Okay, so now let's look at 1, 2, 3, 4, 5, 6, 7, 8. Phosphorus has the octet met. That's what I meant. So phosphorus has the octet met. Okay, I made a mistake in the total valence electrons. It's 26, not 24. So when you do that, the remaining 2 electrons that are left after you finish putting on the oxygens, they go on phosphorus. And these are the ones I meant. These ones. Okay, so now let's look at this one. So what are we going to do? Remember, we have placed all the 26 electrons have been used. 1, 2, 3, 4, 5, 6 on this each oxygen, 18 and 19, 20 on phosphorus, and then the remaining 20, 21, 22, 23, 24, 25, 26 is the single bonds. Okay, so these have been used, all of them, 26 have been used. So now there is, and we checked it, that the phosphorus octet is met. Phosphorus is making 3 bonds. Phosphorus is capable of making 3 bonds. Oxygen is unable to make 2 bonds, but oxygen's octet is met. And always remember, we have these charges. We have these charges. We need to place these 3 charges because oxygen is not able to place, but to make more bonds, or so we will just put the negative charge here, and a negative charge here. So you see all these charges, this is charges, will have to bear the charge in this case. Okay, so now let's look at this one is phosphorus. Oh, okay, phosphorus, lone pair on the top, oxygens will go here. Okay, and then you put single bonds here, and these guys will be holding the charge. 1, 2, their octets are met. They're not making the double bonds, but they will indicate in the electronic world to say, hey, we are looking to bond with a double bond, like or another bond. We need 2 bonds. So they will be indicating that by holding the charge, these charges. Okay, and that is the Lewis structure for phosphite. So polarity. Now polarity is another thing. One is the lone pair on the central atom. That is why it's polar. Lone pair on central atom, which is phosphorus. That's why it's polar. Second thing is it also has a charge. Overall, the molecule has a charge. Okay. So because of the charge, this whole thing becomes because of this is a polar molecule. Okay. There is uneven distribution of charge. Okay, it's a polar molecule. And that also indicates in the atomic world that these charges are looking, these atoms are looking to bond. Now the shape. So shape is AX3E1. As you can see, there is phosphorus, there are 3 oxygens, and there is 1 lone pair on phosphorus. So AX3E1 corresponds to the shape on the table. Which shape? So back here. AX3E1. On that table, you will have to see it again. AX3E1. AX3E1. Internally, it will be tetrahedral. And then Otherwise, it will be pyramidal. Okay, the molecular shape is pyramidal, like a pyramid. So here we see the, sorry, molecular shape of the molecule is pyramidal. Okay, pyramidal. Clear? So like phosphorus is inside, lone pair on the top, oxygens on the side. All right, guys. So this part right here is the, like a pyramid, like that. All right, inside, all this, like inside. Clear? So shape, polarity, structures, drawing the Lewis structures, those things. Okay, so I'm going to stop the recording for this part because this was very intense, and the other one will be small, not very big. So